Okay. Okay, so it seems that it is working now. Good. So great. So I think it seems that it is working now. Okay. So let's talk about the result that we had so far for fixed parameter tractability. So we talk about ETH, and we mentioned that under ETH, for the K-clique problem or K-independent set problem, in which we want to see whether there is a clique of size K or an independent set of size K, there is no 2 to the little of K times n algorithm. So no such algorithm. That is for K-clique. Or K-independence. Here there is a, and this is under ETH. Good. Here I want to say a stronger result. What is the result? It said that assuming this is in Stack 2004. It said that assuming ETH, the same assumption, there is so here for clique is maybe is a result, but it is not the strongest form. It says that under ETH there is no f of k n to the little o of k algorithm for K-clique for any computable function f. So this gives a better thing. So it's saying not only it is no 2 to the little o of k times n is possible, indeed no f of k n to the order k is little o of k is possible. Essentially, it means that you need to solve, if you want to solve the K-clique, you need n to the k. And n to the k is easy because you are just choosing all subsets of size k and see whether any of them is clique or not. And say this one under ETH, that's the best thing that we can do. So that was a stock paper, but the proof actually is nice. So I will just mention the proof here. And you are hearing me well, correct?
Yes, yes.
Great. So let me just go there. Go. Okay, so what is the proof? Maybe a little bit up of the statement here as well. Good. Okay. So assume that you can solve the K-clique problem in some time f of k. So if it is little o of k, it means what's the meaning of that? It means that n to the k over s of k, because it is little o of k. So it should be something, some function of k, which is essentially greater than 1, s of k. And here, s of k should be a monotone increasing unbounded function. So that's essentially the interpretation of this statement. If the counter positive of that, so if there is, assume that there is such an algorithm. So by contradiction, assume such a thing. So if little o of n to the k is possible, like n to the little o of k is possible, then that would be the running time. Now, we are using this algorithm to solve a tree coloring of n vertex graph in time 2 to the little o of n. And if you remember, we talked about the SAT problems. And then from SAT, we mentioned that SAT cannot be solved in 2 to the little o of n or little 2 to the little o of m, where m is the number of clauses. And from that, we could get the tree-coloring hardness, that the tree-coloring on an n-vertex graph cannot be done in better than 2 to the little o of n. This is just some definition. Let k be the largest integer such that f of k is less than or equal to n, and k over s k to the k over s of k is less than or equal to n. So we can just define k, the largest k that has this property. And this now you can define in that way, k is equal to k of n. So for any n, you will find the largest k, and that would be k of n. So you can see that this function is also monotone, increasing, and unbounded. Like when n becomes larger, then k becomes large. Now, what do we want to solve? So we want to solve tree-coloring on n-vertex graph G. So a graph G is given to you. Now, what do? We split the vertices of J into k groups. So these are k groups. And each of them has n over, the number of vertices on each of them is n over k. Good. Now, so that's the thing. Now we construct a graph G. So what is the graph? Sorry, we create a graph H. Now, each vertex in this graph H is corresponding. So each vertex here is corresponding to a proper tree-coloring of the vertices. So for each proper tree-coloring of the first group, or like actually from each group, we are putting one vertex. So there are lots of ways that we can do it: the first group, the second group, and all the groups. So these are, each of them is a proper tree-coloring. Proper tree-coloring of that. So here, n to the k vertices here. So for this n to the k vertices, we can do it differently. So this is, the first way would be like this for this guy. The second way would be like this, and so on and so forth. So for each of these k groups, that each of them has n over k vertices, for each proper tree-coloring of this set of vertices, I'm putting it one vertex in graph H. And then I will connect two vertices here in H if and only if they are not contracting. There is no conflicting. What's the meaning of that? So if, for example, if this vertex, I will, in this particular coloring, I will give it 1, and this guy has another vertex which is 1, and there is an edge between them. So it means that, so if this guy, so if this is a corresponding coloring here to this coloring, which is X, and this is another coloring which is corresponding to this one, Y, then there is no edges here. Because these two are conflicting, because both of these two vertices that they have an edge in the graph, they got 1. Good. So that's the one that we don't put an edge. Otherwise, we will put an edge. Now, we are done. So this is the graph G from this graph H for each. So this is like a little bit different from the type of reduction that we have seen it. But this is actually quite interesting and short. That for each coloring, if you are putting a vertex, for each coloring of each part, we are putting a vertex, and two vertices have an edge if there is no conflict between them. And we don't put any edges between these guys as well, because they are all corresponding to coloring of one of these parts. Is this clear so far? Any question? Good. So now, what does it say? Yeah, go ahead.
So what is this function k of n?
So a k of n is the inverse of this. You see, this k equal to k of n. So we will define for each n, you define largest k that satisfies these two properties.
Oh,
good.
Okay.
And then k is equal to k of n. So it would be a function of n because n increases, then k increases as well.
Okay.
Good. Now, having done that, now we are almost done. Note that any clique, if you have a clique here, essentially it means that this is a proper coloring because this part is this is a proper coloring of the first part. This is the proper coloring of the second part. This is the proper coloring of the third part. And there is no conflict between them. So it means that all of them can be colored at the same time. It means that this is a tree coloring of the whole graph. Now, okay, and how do we, the interesting thing is that on this graph H, we are using the algorithm that we had that could find the clique in this f of k times n to the k over s of k. That algorithm, we use it to find a clique here. So so we see that whether there's a clique of size k or not. If there's a clique of size k, essentially it means that there is a, that actually exactly means that there is a tree coloring of the graph G. Now let's see what is the running time of this algorithm. So the running time of this algorithm is f of k times v of h to the k of s of k. That's a, that's a running time that we are assumed essentially that there exists such an algorithm. Okay, now here we know that f of k is less than n, and we have partitioned into k groups. So for f of k, I will just put it n. Then what is the number of vertices of h? So the number of vertices of h is k, because we have k groups times. So this is the number of vertices of h. Number of, essentially this is the size of v of h. So we have k groups here. And for each group, how many coloring is possible? 3 to the n over k. Why? Because n over k vertices exist in each of these groups, and each of them can have 3 colors. So 3 times n to the k. So that's the number of vertices of h. And then to the power of k over s of k. So that's, we have this inequality. Then we just expand this one, would be n times this times this. Now, k to the k over s of k, that is, we have assumed that it is at most n as well. So we will put it another n here and one n here. And here, so it would be n squared times 3 to the n over s of k. And this, the whole thing is actually little of 2 to the O of n. Why? Because, here we have essentially first, for this, n to the 2 is just the little O of 2 to the little O of n. So that is really, this part is 2 to the little O of n. So n to the 2 is less than that. Now, what about this one? This one is also, you can write, instead of 3, write it 2 log of 3 n. So this is the log of 3 n over s of k. Good. And because here, so we have just only constant, because it is a log base 2 of 3. So that is just some constant. This is a constant. S of k is little o of k. So that would be essentially, that's the reason that we get the little o. So we have some little o and some little o, both of them, the base is 2. So it would be 2 to the little o of n. And that is a contradiction. So that's the whole proof, actually. That was a stack paper. That was a nice result. And that's it, that the ETH, essentially, if we are assuming ETH, it implies that for clique, there is no algorithm better than f of k times n to the little o of k, which is stronger than, so we had this result that there is no algorithm of 2 to the little o of k times n, but this is stronger. What does it say is that for K-clique, this problem is not fixed parameter tractable. You cannot get f of k times n to the some constant c, but it is actually more than that. The only way that you can solve this problem is that you just do it n to the k. And n to the k is trivial. Just take all sets of size k and see whether any of them is clique or not. So you cannot do any non-trivial things, assuming ETH. Of course, the ETH, the question is that, I mean, ETH in some sense assume that also for SAT there is not no algorithm of 2 to the little o of n. So far, we don't have such an algorithm. So if you assume for SAT we don't have such an algorithm, for clique also you cannot do anything better than n to the k, even to see whether there is a K-clique or not. Does it make sense? Good. So let me clear all of this. So what is the implication? If you have some kind of parameterized reduction from K-clique, so if you have some kind of parameterized reduction from K-clique to any problem, other problem x prime to another instance x prime g of k, then here essentially for this other problem, this implies that f of k n to the g inverse of k, there is no such algorithm, because for clique there is no algorithm better than f of k n to the order k. Generally, when we do this reduction, this g of k is just linear in k. So g of k is c times k. So in that case, I mean, the below up in the parameter would be linear. So in those type of problems, so for example, this type of reduction works for, so you can get this reduction for set cover, heating set, connected dominating set, independent dominating set itself, and partial vertex cover. So these are a set of problems that for them, there is such a reduction that when you reduce K-clique to, for example, K dominating set, we discussed that dominating set is a harder problem than clique or independent set. So when you do the reduction, the G of K would be C times K in the reduction. So in that case, it means that there is no such algorithm also for these problems. There is no f of K n to the little o of K for dominating set or all other set cover, etc. So essentially, either it means that either the problem for lots of this natural problem, either there is a fixed parameter algorithm, it means that f of k times n to the c is possible. Otherwise, the best way, assuming ETH, is to just consider all subsets of size k and see whether it is a dominating set, it is a set cover, it is a independent set, it is a clique, etc. However, if we have for some parameter the below up in the when you do the reduction from actually from k, if we go g of k is actually k square, then actually implies that there is no f of k n to the square root of k. So we will talk about some of these problems later. But for now, lots of them were just this type of form, which is the linear part. Good. So what do we have for planar graph? So for planar graph, we have actually some more results. So there's a standard reduction from tree coloring in general graphs to planar graphs, to planar tree coloring graph. So what's the meaning of that? It means that if you want to, again, reduction from this tree coloring in general graph. So to solve the, actually, it shows that solving planar tree coloring is as hard as tree coloring general graphs. And again, planar graph is a graph that you can draw. It's the graph such that there is no crossing of the edges in the graph. So for example, there's a crossing here. If these are the vertices, so this is a crossing. So there is no crossing for planar graphs. So no crossing in planar graphs. Good. And the main idea is this one. It is something, it is called crossover gadget. So what's the problem with a non-planar graph? The issue is that, as I mentioned here, it might be some crossing. However, there is this crossover gadget. That's a very useful one. So this is the crossover gadget. What are the properties of this crossover gadget? So the issue is that so if you have a graph that has a crossing, you need to make it uncrossing, to make it planar, you need to uncross these edges. So for each crossing of this graph, I will put so each crossing, I will put this gadget. That is the one that I mentioned. So anytime that something is crossing, I will put this particular gadget. What are the properties of this gadget? Is that in every tree coloring of the gadget, opposite external connectors have the same color. So if you can, if you want to color this gadget with tree colors, that's a very interesting thing. Always these two guys have the same color, and these two guys have the same color. If you want to do it with tree color, you can check it. I mean, why does it happen? Yeah, and vice versa. Every coloring of the external connectors where the opposite vertices have the same color can be extended to whole gadget. So this is if and only if. So as long as, so this guy maybe becomes, I mean, somebody may tell you this is G, and this is R, this is R. Then you should be able to correctly, color the vertices inside with three colors. So as long as the opposite side have the same color, this is if and only if. If there is a three coloring, they should have the same size, the same color. And if somebody gives the same opposite sides the same color, then we can extend it to the internal vertices. Good. Now, what is the interesting thing? For example, here, this is the interesting part. So if we have this vertex, you can, if you use this coloring, this crossover coloring, that actually guarantees that. So, because in some sense, this is the intuition. Anytime that you have a color here, we have the same color here. So if we really want that if you have some color here, we have the same color here. So when we start from this guy, and so if we are starting with the color R, then we have the same color R here. And say if this is this one also the color R, so in that case, this should be at the end. So G and R should be a different color. So that guarantees that, in some sense, these local properties, when we put these graphs on the crossing, guarantees that two vertices of the original graph, that they have an edge, and we put, no, they don't have any edge, direct edge, but they have lots of these crossings. But because this crossing, they have this property that they make sure that this, essentially this original endpoints of these two colors, they should, all of them should have, these two guys should have the same color. because this crossover things actually make sure that the colors are transferred over crossings. That's somehow the whole idea. Now, good. Now, if you have, now let's see what are the things that we have. So this is the way that shows, this is the interesting result, that tree-coloring of planar graphs is as hard as tree-coloring of general graphs. Lots of planar graph problems are much easier than general graphs, because these graphs, I mean, you can put them essentially in the plane with no crossing, and that generally helps to design better algorithms. But for tree-coloring, there is no difference. Now, let me clear everything. Good. Now, what does this one implies? Good. So when we are doing this, so in this reduction from tree coloring in general graph to tree coloring of planar graphs, we are for each essentially for each edge, you can see that I mean, we are introducing the number of vertices. The number of vertices in this new graph would be so if the original graph is G, this is the one that we want to do coloring for, that tree coloring of. This is the general graph. So this is a tree coloring for G, which has say M vertices and M edges. Then this new graph G prime that we are doing, this is the tree coloring planar. So when we do that, the number of here, the number of vertices and the number of edges of this graph, because M square became M square and M square. So in some sense, because each crossing of these edges, we are putting like because this graph had M vertices and M edges. It is easy to see that, I mean, each edge can cross M other edge. So in that case, the number of crossing, the number of these new vertices that we are adding, the total number of vertices that we have in this planar graph would be M square, and the number of edges would be also M square. So what do we have here? So we have started from 3 sat. Let me just. Yes. So here we have started from 3 sat. We discussed this one previous time. So we have started from 3 sat that has n variables and m clause. From that graph, we could create another graph G and order m vertices and order m edges that we discussed previous time. And using this reduction, we can get a planar graph that has order m square vertices and m square edges. Now, because we have just changed the parameter, so because we had this essentially m here, it goes m square here. This implies that assuming ETH, there is no 2 to the square root of n algorithm for tree coloring of n vertex planar graph G. So again, we knew that there is for 3 sat, there is no 2 to the little of m. So there was no 2 to the little of m for 3 sat. That essentially, because we are doubling here, it implies that there should be no 2 to the square root of m algorithm for tree coloring. Tricoloring of planar graphs. Good. So that's the result that we will get it. So, what's the meaning of that? The meaning is that for general graphs, there is no 2 to the m. So here it is m. So for general graphs, no 2 to the m tricoloring. So for planar graphs, for general graph, we know that there is no 2 to the little o of m algorithm for tricoloring. And again, m and n are the same in this graph that we are. So m and n are essentially the set of vertices in this case. So for general graph, we know that there is no algorithm better than 2 to the little o of m for tricoloring. What's the meaning of that? Again, it means that if you want to do tricoloring, just try all possible tricoloring and see whether any of them is valid or not. Again, under ETH. Here, for planar graph, we have something a bit better. In terms of hardness, we have a bit weaker hardness. There is no 2 to the little o of m tricoloring for planar graph. So it means that instead of 2 to the order m, we can do it 2 to the square root of m. And indeed, this result is tight. So in some sense, for planar graph, we can have more efficient algorithms. So first, we have this hardness that there is no 2 to the square root of n or m here. N is the number of vertices. Algorithm for all this problem, for k independent set, k dominating set, k vertex cover, k partial feedback set, and k feedback vertex set. However, these results actually are tight due to this theory that we have. It is called bidimensionality theory. So for these guys, for any k version of them, there is nothing better than 2 to the square root of k. And indeed, there is such an algorithm. So for planar graph, lots of problems that, for example, vertex cover, it has 2 to the k n for general graph. This is for vertex cover. That is for in general graph. For planar graph, we have an algorithm of 2 to the square root of k times n. So this is, again, this is the VC, this is the general graph, this is the planar graph. So we can do better, essentially, planar graph, and that's the tight things. Good. So let me. So let me define another interesting problem here. This is also another problem that this is some kind of problem that the people are use it a lot to get hardness, especially for planar graphs. So I just defined the problem. Okay, so in this problem, it is called a grid tiling. So it is introduced by Daniel Marks in 2007. And what is this grid tiling problem? So the grid tiling problem is this one. You are given a k by k matrix and a set of pairs, Sij, which is d times d. I mean, for some d. D generally is n, say. Now, you want to find for each, so each, this is k by k matrix that I have mentioned. This is k by k. Now, so for each cell of this matrix, a subset of these pairs is given. For example, here we have d is equal to 4. So each cell of this matrix has a subset of this one. For example, this one has 1, 1, 3, 1, 2, 2, 4. This one has 5, 1, 1, 4, 5, 3, and this is 1, 1, 2, 4. So for each cell, a set of this subset of pairs are given. You want to, from each of these guys, from each cell, you want to select exactly one of these guys, one of this one. So such that we have this property. All vertical neighbors agree in the first coordinate. So for example, here you see we are selecting this guy, we are selecting this guy, we are selecting this guy. All these vertical guys are sharing 2. The first coordinate is 2. And all horizontal, they should share the second coordinate. So here we are selecting 2, 4, 1, 4, and 2, 4. As you will see, all of them have the same. So these guys all have the same second coordinate. And these guys all have the So the question is that, so what is the input? The input, as I mentioned, is K by K matrix, and for each cell, a subset of these pairs. The question is that, is it possible that for each cell, we are selecting one of these guys, one of these pairs, such that we have this property? For all horizontal guys, all of them share the same vertex in the like the first coordinate, and all horizontal one have the same vertex on the second coordinate. Good. So, and you can actually solve, it is easy to see that this problem actually, there is a reduction from K-clique. What's the meaning of that again? We can solve this problem using K-clique. How come? For each I equal to J, for diagonal parts, I will just put it X. So here D is equal to N. Now, for each diagonal I equal to J, so K, of course, is K-clique, we have a K by K matrix. For each diagonal, here we have XY belongs to Sij, if and only if X is equal to Y. What's the meaning of that? It means that for diagonal, I will put it 1, 1, 2, 2, to NN. So that's for diagonal. What about for non-diagonal? So if I is not equal to J, so for anything which is not diagonal, I will put X, Y belong to Sij if X and Y are adjacent in G. So essentially for anything, so for diagonals, is this diagonal? As we discussed, I will put it just 1, 1, 2, 2, NN, I mean, all of these pairs. For everything else, I've just put the set of edges of the graph. Now it is easy that if there is a K-clique, then it means that you need to select essentially just those K vertices. If you select those K vertices, then, so if you select those K vertices on the diagonal, the vertices, so for example, if you select the vertex 1, 1, 1, then you will choose the pair 1, 1. If you select the vertex N, then select this one, NN, in this diagonal. Then if you select this one, then you can see that because we are putting set of all edges as the pairs, then we have this property that we discussed, that all the horizontal ones share the second coordinate and all the vertical ones share the first coordinate. So this problem, you can get it the hardness from clique. So this problem is W1 hard, because clique was W1 hard. So, and there's such a simple reduction that you can get it. So because of this theorem, because of this reduction that we mentioned for the clique, this problem is this K by K grid tiling. This problem is actually is W1 hard. And assuming ETH, you cannot do anything better than f of k n to the little of k for this problem. So this result that obtains for essentially this problem is very important results to get hardness for planar graphs and general graphs. So in some sense, this is the problem. So this is, of course, it is almost equivalent of K-clique. It's a bit different, but it is a more modern way to prove very strong hardness for problems, especially on planar graph, but also on general graphs. For example, you can get all this hardness using this problem. This is the least coloring on planar graphs. Multi-way cut on planar graphs with K terminals. Independent set for unit disk graphs. So unit disk graphs are also very similar to planar graphs. So essentially, these are a set of it is like the unit disk graphs or disk graphs. Generally, it means that you are putting some disk in the graph, and two vertices have an edge if and only if they do not intersect. So it is very similar to planar graph. Disk graphs or unit disk graphs or planar graph, they have very similar properties. All of them, the hardness for, like for example, independent set for this graph, or the multi-way cut or least coloring, or another problem is planar directed Steiner first. All of them are using this new problem, K by K grid tiling. So this K by K grid tiling is a very important problem, actually, if you want to use for planar graphs or even for general graphs, to use this one to get the hardness. So there is a proof for directed Steiner forest that I defined it before when we talk about approximation algorithm. You can read it here, but I don't want to go through the details here because of interest in time. So let's go to some other things that I wanted to talk as well. Any questions so far? Great. So far we talk essentially for lots of fixed parameter algorithms, and we mentioned that in some sense the problems, either there is a fixed parameter algorithm like for vertex cover that you can get f of k times n to the order 1, or if there is no such algorithm, assuming ETH, the hardness essentially for stat, that n variable stat, you cannot do it anything better than 2 to the little o of n. Then the best way for this problem also, if that you want to see a solution of size k, just try all subsets of size k and see whether any of them is a solution or not. You cannot do anything better than that. So either the problem is fixed parameter tractable, it means that there is a good algorithm, or if not, that's the best way to do that. You cannot do anything better than that. And for planar graphs, the bonds will just improve essentially. Instead of 2 to the k, it becomes 2 to the square root of k, and we have similar results. Good. Now, what about kernelization? Also, we discussed at the beginning of the class that if the problem is fixed parameter algorithm, if and only if there is a kernel, and kernel was a sketch of that solutions. So you can essentially, instead of solving the problem on the whole n vertex graph, you could get another graph such that its size is order essentially g of k. And this is h of k. So if you had a graph of size, so the original instance is nk, then you can turn it into gk hk. And important thing is that the n becomes g of k. So you don't have n anymore, you have, that would be g of k. And kernelizations, so this essentially means kernelizations. And this is equivalent of fixed parameter algorithm. Now let's see, and we have talked about, if you remember, we talk about vertex cover, and for vertex cover, actually we gave a kernel of size k to the same k. K to the 2 was the number of edges. So interestingly, this is the result that we have for kernelization. So for any epsilon greater than 0, vertex cover problem parameterized by the solution size does not admit a polynomial kernel bit size in terms of number of edges in the order of k to the 2 minus epsilon. So these things that we have seen for vertex cover, VC, I will say vertex cover, that we obtain k to the 2 number of edges and then the parameter k was the same. That was essentially the best solution we could get it. So this is the important results. And this NP is not subset of CoNP slash poly. So CoNP slash poly is very similar to CoNP. Essentially just this one, it is the same as NP is a subset of CoNP, that we don't believe it is the case. So assuming that NP is not subset of CoNP slash poly, then there is nothing better than k to the 2 size graph when you do the kernelization for vertex cover. And if you remember, we discussed that the kernelization would be, so here the number of edges was k to the 2, but in terms of number of vertices, actually we could get 2k. So the number of vertices was 2k, but the number of edges was k squared. But essentially it means that still the size of this graph is k squared. Now, so using this problem, you can actually get hardness. So using these things that I have mentioned, you can get hardness for other problems. So another problem it is, for example, is called feedback vertex set. So what is the feedback vertex set? So the feedback vertex set is that you are given a graph and you want to delete a set of vertices such that the graph does not have any cycle. Good. So in the vertex cover, you wanted to select a set of vertices such that each edge has one vertex, one of its endpoints is in the set. Here in the K vertex cover, you want to select a set of vertices such that so deleting the minimum number of vertices to make a graph cycle free. Now, you can say that for the feedback vertex set, also there is nothing better than k to the 2 size kernel. Why? Consider the vertex cover. So I want to say that the vertex cover can solve, the feedback vertex set can actually solve vertex cover. That is very simple. So consider each edge in the vertex cover instance. I will put a new vertex. I will put a new vertex for each edge in the vertex cover. So this is feedback vertex set. I will still keep this edge. And this is vertex cover. So in the vertex cover, there is a vertex, there is an edge between U and V. In the feedback vertex set, I will keep that edge. Also, I will add a one vertex for this guy and just connect it to both of them. Now, in the feedback vertex set, in the vertex cover, the goal, as we discussed, in your solution, you should either select this, one of these endpoints, U and V should be in the solution. In the feedback vertex set, it is easy to see that. So this is a cycle, so we need to kill it. So to kill it, of course, we can select this vertex, the top guy, but it is always better instead of this top guy, kill this guy or this guy, either U and V. Because the top guy does not help you in any other way. You can show that there is an optimum algorithm that always essentially select U or V, not that this W guy. The W guy will not be selected actually. So because you need to, so in some sense, killing these cycles, these triangles on the edges would be equivalent of killing, selecting one vertex from each edge on the vertex cover. So then we know that for feedback vertex set, because of this simple reduction that I have mentioned, you cannot also get any kernel of size better than K square. Good. So let me clear this one. So there is, you can do this kind of reduction to get for kernel hardness as well. Yes. Let me actually. So that was also another interesting thing that I wanted to mention. So, we discussed that again. If the problem is fixed parameter algorithm, then there should have a kernel, and the kernel, the size of the kernel should be f of k, the parameter. But here, as we have seen, for example, the kernel size can be k square. For some other problems, especially on planar graphs, you can see that the kernel size actually can be linear in k, the parameter. So the size of this graph that we are creating here, for example, for vertex cover or for feedback vertex edge was k square. For some other problem on planar graph, or you can get even just linear in k. The question is that, can we always get a polynomial in k or not? And that's actually interesting thing about Steiner tree. For a Steiner tree, what is the Steiner tree we discussed before for approximation algorithm? So it asks minimum number of edges which connects a terminal set. So you are given a graph G and a set of terminals, and you want to say what is the minimum number of edges such that you can connect all of these terminals. So you can show actually a Steiner tree parameterized by the size of the tree, the size of the solution, does not admit a polynomial kernel unless NP is a subset of co-NP/poly. Again, co-NP/poly is just some variation of co-NP. You can see the exact definition in the Wikipedia or in the book. Good. So for some problem like a Steiner tree, you cannot actually get a kernel whose its size is polynomial in k. The size of the kernel itself would be exponential. This also you can, so this is, so for a parameterized problem, you can parameterize it by difference. Here is the parameterized by opt. But even if you parameterize by the number of terminals, so if there are, I have at most k terminals, still you can say that this problem it does not have, so Steiner tree parameterized by optimum or parameterized by the size of the number of terminals, the vertices that you want to connect, still it does not have a kernel of less than 2 to the k. So the kernel is exponential in some sense. These are some other problems that is also, these are interesting. So you can actually say, if you consider a Q sat, so for any Q greater than or equal to 3, like 3 sat, 4 sat, 5 sat, for any Q sat, the Q sat problem parameterized by the number of variables n. So if you say that this is the things, and the number of variables n is the parameter, the kernel size cannot be better than n to the q. So in some sense, this says that for this q sat, there is nothing more interesting than n to the q, and n to the q is all possible clauses that you can have. The same thing also we have it for deheating set. So deheating set problem is a generalization of vertex cover. So in the deheating set problem, you are given some sets of size D. So these are the sets of size D. So size D. So these are the sets. So these are sets of size D. A number of them are given to you. And then you want to select minimum number of, and each of them have some element like 1, 2, 1, 3, 4, and so on and so forth. You want to select the minimum number of, vertices, minimum number of elements, such that you will hit every set. So it means that from each set, at least one element is selected. You can see that this problem is a generalization of vertex cover. Why? Because in vertex cover, you only need to give the set of edges as the input. Each edge has only 2 elements. So the edges are given to you, and you want to select, so which edge is between 2 vertices. You want to find minimum number of vertices such that you will hit every set. Every set would be every edge. So the 2 heating set problem is the, 2 heating set. This one essentially is, I will say, is equivalent of, or at least can solve vertex cover problem. So 2 heating set actually can solve vertex cover problem. Actually, it might be equivalent. So this is for 2 heating set. So we knew that for a vertex cover, that was a 2 heating set, there is nothing better than k to the 2. This other theorem says that if you, so this is for vertex cover, which was 2 heating set. Now, for D heating set, if the size of these guys can be D, then you cannot get anything better than k to the D. So this, so there is no sketch of better than k to the D. So this is just a generalization of this vertex cover. If you consider the heating set is a very important problem. And this heating set, if you consider that one, then you cannot get anything better than k to the D. Good. So that's a summary of the results for these problems, for these generalizations. And let me just talk briefly about two other things. So there are 2 other problems that we are. So this concept of fixed parameter algorithms actually has been used for other cases as well. So and can use essentially for combination with other problems. For example, what is the general idea? When we talk about streaming algorithms, so we had some stream, and we were talking about the space that we need to solve the problem. And we talk about the space, the minimum space that we have it even for finding a cycle, or we needed order n. And we had this semi-stream. So this concept of fixed parameterized streaming, what is that? It says that maybe if the size of the solution is small, then I can actually have some space which is small. This is actually the interesting things that we have introduced. The first paper on this thing, now there are several results on there, that we say that parameterized streaming is a set of streaming problems such that the space that we need for a parameter k is indeed order k times polylog n. So polylog n, we need to have it because any number between 1 and n, if you want to have just any number between 1 and n, you need at least log n bits for that. So that is somehow unavoidable. But other than that, we want that the space be order k. So for example, in this paper, we show that for a matching, for a maximal matching or vertex cover, you can actually, so if this is the, so what is the vertex cover? Again, the streaming version, that the set of edges are coming and you want to just select a set of vertices such that you will cover all edges. So if we have this assumption that the size of the vertex cover is at most k in this graph, then actually the space that we need for these problems would be order so that would be order k square. So for vertex cover, interestingly, you can get a parameterized streaming algorithm. So there is this relation between parameterization and streaming algorithms. Another connections that we have it with parameterizations and different type of algorithm that we have is this type of algorithm. Fixed parameter, this is actually very trendy nowadays. The people are working. Again, this is the one paper that we had the first paper on that topic. So this is the fixed parameter and approximation. So an FPT approximation algorithm is some approximation algorithm that the ratio of this algorithm, so it has some ratio rho, and this rho, I mean, can be actually function of optimum. The optimum is the parameter here. So the ratio should be, I mean, some rho of opt, and the running time. So this is the ratio that should be like this. Also, the running time should be parameterized by optimum. For example, what is this things? Good. So let me just. So these are some initial results that we had it actually. So this is the things. So what do we say that we say? So as so assume, I mean, unless NP is sub-exponential, which is essentially very similar to ETH. So what do we have for the K-clique problem? There is no FPT approximation algorithm such that its ratio is opt to the 1 minus delta, and running time is 2 to the opt to the f times polynomial in it. What's the meaning of that? It means that if you consider the K-clique problem, so K-clique, I mean, you want to find the K-clique, but maybe you want to get approximation for K-clique. So can we, maybe if the K-clique has size k, maybe you want to find some K-clique which has a smaller size, but there's still some function of k. So this one, it says that there is no algorithm for K-clique unless NP has a sub-exponential time algorithm, such that the approximation algorithm of this fixed parameter, this approximation algorithm is opt. So if opt is, I don't know, 10, you cannot have any 10 approximation for the problem. In running time, 2 to the opt. Again, here, for example, 2 to the 10 times n. So if optimum is k for K-clique, then there is no k approximation for the problem in time. Or like say, for example, if the optimum is k, there is no SQR root of k approximation for the problem in running time 2 to the SQR root of k. Similar results can be obtained also, and we obtained it for these problems like exactly similar result for dominating set. So this was essentially for clique. This also for set cover and dominating set are the same essentially. For set cover and dominating set, you can get the same result under some, again, complexity under ETH. So this was ETH. This is ETH. But here there's another conjecture called the projection game. Under this condition, you can show that for set cover or dominating set, there is, again, nothing. So if you cannot get anything like opt approximation or K approximation in time 2 to the K algorithm. So unless you want to pay exponential in K, at least this theorem says that you cannot get anything better than K approximation. So there is this. This was the initial result that we had it in about connecting fixed parameter algorithms and approximation algorithm. And nowadays, actually, there are lots of other results for these problems. These are the results for different problems, for cut problems, for connectivity problems, and others. So this kind of fixed parameter approximation algorithm is a trendy thing nowadays as well. There are several papers in pseudo-Fox stack, for example, on those type of problems as well. Anyhow, so this concept of parameterization, that there is a parameter K, and you want to get, if the K is a small, the running time should be a small. That has been used in streaming as well as in approximation algorithm, and possibly can be used for other areas as well. Good. So this actually finishes this part. Let me just stop share. So yeah, this finishes this concept of fixed parameter algorithms, hardness, and there are some other things, like, for example, that there are other topics which are in the book, and you can read more about them in the book. So let me. Okay, so we are finishing this session, and see you later. Bye.